Welcome to this presentation on instance-dependent sample complexity bounds for zero-sum matrix games. I am Arnab Maiti, and this is a joint work with Professor Kevin Jamieson and Lillian Ratliff. In this presentation, we mainly deal with 2 plus zero-sum matrix games. So, let me first introduce you the setting. So, consider a matrix A with n rows and m columns. Let delta m denote the m dimensional probability simplex. Then, in a 2 plus zero sum game, a pair x star y star is said to be a Nash equilibrium if this following inequality holds true. So, if you take any pair x comma y, then this inner product x a y star would be less than this inner product x star a y star, which would in turn be less than x star a y. So you can interpret this inequality with respect to with respect to two players, one being row players and another being column players, and each of them is playing the strategy x star and y star and is trying to see whether it can improve upon its strategy or not. And if it cannot, then we say that we are in an equilibrium. Now let this inner product x star a y star be denoted as va star, and this we call as the value of the game. Due to this famous von Neumann's minimax theorem, we have the value of the game equal to max over all x, min over all y, x a y, equal to min over all y, max over all x, inner product x a y. So in some sense, the max min value is same as the min max value. And because of this, one can formulate any zero sum game as a linear program and find the Nash equilibrium. Now, the setting that we'll be focusing on will be a noisy setting where the matrix A is not directly available to us. Instead, what we can do is we can query an element ij of the matrix A and receive a value xij, where xij would be sum of the actual value aij plus some eta, where eta is a zero mean one sub-Gaussian noise. Now our aim is to compute some kind of approximate solution by sampling as less number of elements as possible. So here are two solution concepts that we would be focusing on. First is epsilon good solution. So we want to find some pair x comma y such that it is in some sense close to the value of the game. To be precise, if we look at this inequality, so we want that va star minus this inner product x a y, the absolute value of this difference to be less than equal to some epsilon. Now the second solution concept is epsilon Nash equilibrium, where we aim to find a pair x comma y such that these two inequalities hold true. So the inner product x a y is greater than or equal to inner product x dash a y minus epsilon, and inner product x a y dash is greater than or equal to x a y minus epsilon, and this should hold for all pairs x dash y dash. So what this inequality says that the players can deviate from their decision x comma y and gain by at most epsilon. So this is equilibrium up to some value of epsilon. Now, a very well studied area, which is a stochastic multi-arm bandits, is a special case of a noisy setting. And instance dependent sample complexity bounds to find the best arm is actually well studied. So we aim to establish similar instance dependent bounds to find either epsilon good solution or epsilon Nash equilibrium in zero sum games. Towards that, we define few instance dependent parameters for 2 cross 2 games. So first is a parameter which we call as D. So it would be the sum of say diagonal elements and the difference of both of them. So precisely it will be a11 minus a12 minus a21 plus a22. So sum of these two and then difference of them. Next is a parameter which we call as delta min, where we take pairwise absolute differences and then take the least among all of them. Now the last parameter is delta m2, where we take where we consider pairwise distances of rows and similarly pairwise distances of column and take the minimum among them and then consider the maximum of both of them. So to be precise, you take minimum of a11 minus a12 comma a22 minus a21, and similarly you take minimum of this and this, which is this thing, and then you take the maximum of both of them. Now we present our results first for 2x2 games. Suppose the matrix that you're considering has a unique Nash equilibrium, which is not a pure strategy Nash equilibrium. Then under some mild assumptions, we can show that if an algorithm wants to find epsilon good solution with probability at least 1 minus delta, then it should sample at least these many entries from the matrix. Like it should take these many samples from the matrix. So let us go through this equation. So it says that the algorithm should sample a minimum of either 1 by epsilon square or maximum of these two thing, which is 1 by delta min square and 1 by epsilon mod d. So in practice, this is the term which will be less than 1 by epsilon square, because these will be like huge parameters. So if the matrix is kind of well spaced, say 1 0 0 1, then you can expect that you can find an epsilon good solution in roughly 1 by epsilon samples instead of 1 by epsilon square. And we complement this lower bound by designing an algorithm that identifies epsilon good solution with probability 1 minus delta using a number of samples matching the lower bound up to some logarithmic factors. In a similar way, we establish a similar lower bound to find epsilon Nash equilibrium for the matrix game, and this is the lower bound that we require. Lower bound on the number of samples one must query in order to find epsilon Nash equilibrium. So similar to epsilon good solution, we have minimum over 1 by epsilon square and maximum over this particular term. And as usual, we have this delta min square, and this is a different term, delta m2 square by epsilon square d square. So if the parameter delta m2 is roughly of the order epsilon, square root epsilon, then using 1 by epsilon squares, 1 by epsilon samples, we can find epsilon Nash equilibrium. On the other hand, if the matrix is very well spaced, then we would require like something like 1 by epsilon square samples. So this is a bit different from epsilon good solution. And we complement this lower bound by designing an algorithm that matches the lower bound up to some logarithmic factor. Now, if the matrix had a non-unique Nash equilibrium, then under some mild assumptions, we show that we would require 1 by epsilon square samples from the matrix. Now we proceed towards n cross 2 games, and we define some parameters in this space as well. So first we define delta min. So it's the same idea as that of 2 cross 2 games, but we are just extending it to n cross 2 space. So we look at the difference in rows, difference in column, and then take the least over all of them, and this is what it means. Next we go towards a more non-trivial gap parameter. So suppose the matrix has a unique Nash equilibrium x star y star, and it can be shown that if a n cross 2 game has a unique Nash equilibrium, which is not a pure strategy Nash equilibrium, then the support size would be exactly 2. Now, uh, so now the kind of gaps that you can visualize in this kind of framework is you take the y star and you take the dot product of y star with the rows and compare it with the value of the game, and you will start seeing some gaps in those rows which are not part of the support. Now if you rescale a bit by the parameter ri, then take minimum over all such gaps, then you get the parameter delta g. Sorry. Yeah. So the kind of results that we show is that first we considered a 3 cross 2 game which has a unique Nash equilibrium which is not a pure strategy, and we showed that one would require 1 by delta g square samples roughly from the matrix A if they want to find the epsilon good solution. And this lower bound also holds for the epsilon Nash equilibrium as well. Now we complement this lower bound by designing an algorithm uh, that uses like you can say roughly 1 by delta g square samples again, and finds the support of the matrix. And the support would be a 2 cross 2 case as I was specifying earlier, and then we can use the algorithms for 2 cross 2 to find the desired solution concept, whether epsilon good or epsilon Nash equilibrium. So thank you, and please have a look at our paper which is available in the internet.